During the last ice age, the Earth has undergone many alternating cold and warm periods, occurring on a millennial timescale. Evidence for these climate fluctuations were first found in the Greenland ice core. Ice isotopic records with less negative values indicating warmer conditions. The last ice age spanning from 120,000 to about 10,000 years ago. Several abrupt warm-cold oscillations, called Dansgaard-Oeschger events, exist, with temperature changes of 8 to 15 degrees Celsius in a matter of decades. Other cool periods exist, for example Heinrich events, the last glacial maximum, or the abrupt Younger Dryas cooling. Were these abrupt climate changes visible globally? In Antarctica, a new ice core measurement shows evidence for a 1-to-1 match between the Antarctic warm events and the cold stadial periods in Greenland. However, the climate changes in Antarctica are not abrupt as compared to Greenland. This oppositional phenomenon is also called the bipolar seesaw. In the tropics, good paleoclimatic correlation with the Greenland climate record was found in widespread regions as the Santa Barbara or Cariaco Basin, Yemen, Oman, India, and China. All the abrupt changes are preserved in the cores, which suggest a strong involvement of the tropics and a large-scale Asian monsoon change. So there is paleoclimatic evidence for abrupt climate changes occurred coevally in the northern hemisphere and large parts of the tropics, as well as more gradual oppositional climate changes in the southern latitudes. But what caused these climate variabilities? The exact reason is uncertain. Subsequently, 4 physical mechanisms that could be responsible for the climate variabilities are briefly discussed. This is the thermohaline circulation. A favorite explanation for the observed abrupt climate changes centers on freshwater input in the North Atlantic. If surface water at the sites of deep water formation becomes too fresh, then the circulation would weaken or shut off, as the surface waters would not be dense enough to sink. The source of this fresh water could be a change in the outflow direction of meltwater, iceberg calving, or glacial outburst floods. As the circulation is stopped, heat transport out of the tropics is also stopped, resulting in a sudden warming, which may explain the observed bipolar seesaw. Yet it is not clear whether these changes were the cause or consequence of abrupt climate changes. Also, no known climate forcing has a time scale of the observed warm-cold oscillations which could cause a meltwater pulse. An alternative process to explain climate changes are large-scale changes in wind patterns over the North Atlantic. During warmer periods, a meridional north-south oriented flow of the jet stream enables warm air to extend farther north. Larger and thicker ice sheets during cold periods forces the jet stream to shift further south, resulting in a more zonal east-west oriented flow, allowing glacial conditions to extend. At the same time, the intertropical convergence zone is also shifted to the south, which may lead to the observed monsoon anomalies in the tropics. However, it is unclear if a change in the wind pattern alone can explain the climate changes recorded. Another mechanism is sea ice extent, which has 2 strong influences on climate. Firstly, through albedo effects, which changes the energy budget. Secondly, by insulating the ocean from the atmosphere and thus cutting off heat and moisture exchange, which influences feedback reactions. However, sea ice requires some forcing to cause it to change. Finally, tropical ocean atmosphere processes play a key role in global climate, as the tropics are the main source of heat and water vapor on Earth. The content of water vapor in the atmosphere changes the energy budget and may lead to global warming or cooling. Another issue is the cycle of warm and cold sea surface temperature of the tropical Pacific Ocean. A persistent change in a so-called El Niño sudden oscillation generates much climate variability and may lead to a large-scale change. But thus far, it has not been shown how abrupt changes could arise from internal processes within the tropics. So finally, how can the observed abrupt climate changes be understood? There is certainly support for a major role of the thermohaline circulation in abrupt climate change, and paleoclimatic evidence for meltwater events flooding into the North Atlantic. However, there are still major unresolved issues. Thus, a complete understanding of the mechanism of abrupt change requires a thinking about all the processes as components of a global coupled feedback.